right, hello everyone. Welcome. I'm really excited to be here today to kick off the builder stage here at MongoDB.localSF. I'm Kevin Roosevelt. I'm the Director of Engineering here at MongoDB working on search and AI. I've been working on search and vector search for about 7.5 years with a little bit of time working on the architecture of the core database as well. Born and raised in California, grew up on the peninsula and live here in San Francisco now, so really excited to have .local back here in San Francisco and be able to talk to y'all. Been doing a lot of scuba diving over the last 5 years, but I haven't been out in the last 9 months, which has been really sad, but I've picked up sailing in the meantime, which has been really great. And up on the top right is me and my wife in Komodo National Park in Indonesia on a scuba diving trip last year, and then that's my dog, Elphaba. I'm going to talk mostly about kind of the implementation of search and vector search and how it works today. But just at a high level, search is going to give you feature-rich, performance-relevant search. And vector search lets you build intelligent apps powered by semantic search and generative AI. And both of these are deeply integrated into the database and let you have these capabilities without having to do a lot of management. So we're going to dive a little bit into that. Historically, both search and vector search have only been available on MongoDB Atlas. Last year, we launched a public preview of support for community and enterprise. And today, I'm really excited to announce here that we've made source available MongoT, which is the engine that powers search and vector search. So go check that out later today when you have some time between sessions. I'm really excited to make the great work that the team's been working on available for everyone to see. So we're going to talk a little bit about some of the design principles that went into building search and vector search, and then we're going to check out how MongoT works underneath the hood. So when we set out to build search, we had 3 design principles we had in mind. I'm going to just introduce them, and I'll talk about each of them individually. The first was to build a frictionless developer experience. Secondly, we wanted to leverage battle-tested technologies. And finally, we want to make sure that we weren't disrupting transactional workloads with search. So let's look at the first one, a frictionless developer experience. So prior to search, if you wanted feature-rich performant search, you needed to ETL your data out of your database and into a kind of purpose-built search engine. And that's just a lot of undifferentiated heavy lifting that we want to take away from application developers to let them focus on building their applications. And we wanted to do that in a way that would feel native to MongoDB developers. So this is what it looks like to use search. It's really simple. You just run commands just like any other command in MongoDB. Here on the left, you can see how you create a search index, just a simple command run against the database. And then $search itself is an aggregation pipeline stage, just like any other. Run it. It composes with other stages, like you can see here with $limit. And it's that simple. Same story for vector search. Tell it a little bit about how you want to configure the index, configure the data, and then you run your query through the aggregation pipeline stage. So all that, all baked into MongoDB, really that simple. You connect to the database through the same connection string, same way you would application, driver, compass, whatever you're using, and you get to be able to manage those indexes and run your queries just like any other query in MongoDB. Next, we wanted to make sure we were leveraging battle-tested technology. So we want to build on top of mature systems to make sure users could run their sophisticated, demanding relevance workloads. And we also wanted to build a simple system that leveraged the strengths of each of the components in it. So unsurprisingly, MongoDB was one of those systems. May seem obvious when you're talking about building a search engine in MongoDB, but hopefully you'll see that we were able to leverage the strengths of MongoDB to build a search engine in kind of a different way that had been done before. And then Apache Lucene is going to provide us with the specialized data structures and query execution required to build search and vector search. And then finally, we know that transactional workloads are the lifeblood of businesses and applications, and we want to make sure that people are feeling safe to run search and vector search on those same workloads. And search and vector search indexes are computationally expensive to create and maintain. And so one thing we wanted to make sure we did was do that outside of the transaction commit window to keep those isolated. So MongoD is the core database process that handles transaction processing. And our desire to isolate the search workload from the transaction workload, along with wanting to use Apache Lucene, which is written in Java, led us to build a new process called MongoT. And we're going to spend the rest of the talk here kind of peeling back the layers on MongoT and how this works under the hood. So first, let's talk about index lifecycle management. And by that, I mean kind of how indexes are being created, updated, and deleted. We're going to see a few sequence diagrams here today. Let me explain quickly how this is going to work. I hope it'll be a little self-evident. But we have our system here. We have 3 participants in the system, in this case, the application, MongoD, and MongoT. They're going to be sending messages to each other, and then time is going to progress on the y-axis from top to bottom. Hopefully it's pretty clear. So create search index, like I said, is the way you manage search indexes. You just send that to MongoD like any other command. In our system, MongoT is the logical owner of search indexes. So MongoD is actually going to proxy that request over to MongoT. Now, MongoT needs somewhere to store its version of the index catalog. And in doing that, we want a place to store it that is durable, consistent, highly available. And it just so happens we have the perfect system for that, which is MongoDB. And so MongoT is going to insert that information into the database, still being the owner of it, but use it as kind of that reliable store of data. Once that's happened, it'll acknowledge to the database that we've received that request for the search query, which will acknowledge it back to the user. So that's great. We've acknowledged that the search index should be created, but how do we go about actually having a search index that we can run queries on? That's where our replication system is going to come into play. So the goal of our replication system is to maintain an up-to-date version of each configured index. And there's going to be 2 phases that we're going to go through in replication that's going to accomplish that. The first is called initial sync. Initial sync is where we're going to build an index that is consistent with a snapshot of the database at some point in time. And then the second is steady state replication, and that's where we're going to be keeping that index up to date with events that happen after that snapshot. So let's take a look at that. We have our kind of sample collection here, pretty massive one. We've got 5 documents in it. How do you go about building that index and getting this data into that index? The simple thing to do would be to run a collection scan all of the data, and put it into the index. That's nice. It's a very simple mental model. But when the rubber meets the road and reality comes into play, that doesn't quite work perfectly. When you're running a long-running query in MongoDB, the way the execution engine is going to run is it's going to be reading that from snapshots of the storage engine wired Tiger as it progresses. And when you're running a long-running query, the query engine might yield the snapshots that it's running on to pick up newer snapshots as it goes along. That's all fine and good, but what it means is we need to be cognizant of concurrent updates happening to the database while we're running our query. So let me explain a little bit more what that looks like. We're going to have that same system here. We've got our collection on the left, our index on the right, and then we're going to have some events we're tracking happening during the scan concurrently. So we do the first part of the scan, get document 1 in. Then while we're doing the second part of the scan, maybe a delete comes in on document 1, and that document's deleted. While we're doing the next part, maybe document 5, which we haven't scanned yet, is updated to version 2. Now we're going to scan the final part, and we're going to get version 2 of that document in our index. So just visually here, you can kind of see there's a mismatch between the two, where we have document 1 in the index, which no longer exists in the database. But not just that, the version of the index is actually not consistent with the database at any point in time, right? There's never a time in the database's history that both document 1 existed and version 2 of document 5 existed. So we don't have even a consistent snapshot, which is just not a great place to be starting from if you're trying to build a reliable, correct replication system. So what do we do about this? There's a few ways we could go about tackling this. One is to use snapshot read concern, which is something MongoDB provides, which basically tells MongoDB, hey, use a snapshot of the same data the whole time you're running the query, which will turn this kind of fragmented query execution back into that nice logical view that we like to have. Snapshot read concern is great, but if you're running it on very long queries, it can start becoming expensive. And we want to be able to run search index builds on terabytes of data. So this isn't going to be the right choice for our specific use case here. What else could we do? Another option is we could apply all of the events that happened during the collection scan, since events that happened starting before the scan all the way up to happening after the scan to the index. Let's see what happens if we do that. So we'll apply the delete, and that'll remove document 1 from the index. And then we can idempotently apply the update to document 5, and now we have a consistent snapshot with the database. So that sounds a bit better. Let's see if we can actually make this true in reality when we look at how the system works. So if we want to do that, what we're going to need is an ordered event stream of all of the events that have happened since the beginning of our collection scan, right? And luckily, MongoDB is actually already keeping track of these events for us. There's a collection internally called the Oplog that MongoDB uses for its own replication purposes. Secondaries in MongoDB are going to read the Oplog of the primary and apply those events to keep their version of the data up to date. And MongoDB provides a public API called change streams on top of this Oplog where you and your applications can subscribe to these events, which is great. Sounds like we have all the pieces we need here. One piece of information to keep in mind is that the Oplog is bounded in size. Over the history of the lifetime of a database deployment, there's going to be uncountable numbers of events happening, right? And we don't want to keep every event in the history of the database on disk, so we're going to bound that Oplog. Of course, this is configurable for your needs, but in our case here, we're just going to look at a simple example where we have 2 events on is the capacity of the Oplog. And so what's going to happen if a new event comes in? We have our first event that happened on document 1, second event that happened on document 2, or document 5 rather. If a third event comes in, we're going to push out document 1, right? Pretty sane behavior. But what that means is if you are a subscriber to the change stream and you haven't been keeping up with the events, if you haven't read event 1 yet, you have a hole basically in the history that you have access to. And MongoDB is going to tell you about this. It's not going to just blindly tell you, hey, here's event 5. It's going to say, hey, you have a hole you weren't able to keep up. But this is something we need to be aware of when we're building our replication system, right? If we're going to run a really long collection scan and there's a ton of events churning through the system, when we go to apply those events at the end, we might have found that we have not kept up and there would be a hole, which means we're not going to be able to build a consistent version of the index. So our very simple scan and then apply seems like it might not work resilient to any type of workload that's going to be running out there. So what do we do about that? All right, let's take a step back. We've learned some things. What is the goal of our initial sync system now? We want to build an index that's consistent with a snapshot of the database at some time, and we want to be able to build it on huge data sets, and we want it to be resilient to very active workloads during those data sets, right? And we have a nice kind of simple algorithm of scan and then apply that we think works, but might not be resilient in that way. So what MongoT is going to do is it's actually going to take that simple algorithm and apply it iteratively to chunks of the data. So we're going to break the collection down into chunks, and we're going to do a scan of part of the data, then apply events to catch up, do a scan of the next part of the data, apply events to catch up, do this iteratively until you've scanned all the data, and at the end, you should have a consistent snapshot that's actually pretty recent as well because you've been doing the scan continuously. So let's take a look at what that looks like, and hopefully it should be a little clearer. Going to do doc1 scan, no events have came in, so there's nothing to apply. We're going to do the next part of the scan. Now the delete event has come in during that part. We're going to apply that directly now. Do the next part of the scan. During that, the update to document 5 came in. We're going to scan that, and when we do the scan during this initial sync, we're going to treat updates as upserts. So we're going to say, hey, it's okay if the document that we're updating isn't in the index yet. Insert it if it isn't. So we'll do that, and then we'll do the final part of the scan. And likewise, on the scan, we're going to say inserts are idempotent. It's okay if there's already a version of this document in the index. When you go to insert, it might have shown up from an upsert. So if we do that, great, we have a consistent snapshot now, and because we've been applying these events, it's a pretty recent snapshot, and we can transition into steady state replication, which just continues to apply change stream events as they show up. So this is awesome. We have data in our index now, and we can finally do the thing that we're actually trying to do, which is query. And so going back to our handy sequence diagram here, again, we have MongoDB, we've got the application, we've got MongoT. You've seen this part before, ag pipeline stage, just like any query, going to MongoD. You might be able to guess what's coming next. We're going to proxy that off to MongoT to execute the query. So MongoT is going to take that request that's proxied from MongoD. It's going to execute the query. Query execution is a super fascinating topic. We could talk about that all day. Unfortunately, in this session, we don't have time to, so we're going to leave it as a black box for now, or actually a green box on this diagram. But what MongoT is going to do is it's going to take the results of the query execution against its index, and it's going to return to MongoD the IDs of the documents that matched. Search and vector search queries are implicitly sorted by relevance score. We want to be returning you the most relevant documents first. That's kind of the whole point. So it's going to return that information to MongoD as well. In this case, we're running a vector search query, so that similarity score is going to be kind of the representative of the vector similarity that was run against the index. MongoD is going to use that data. It's going to look up the documents in its store from the IDs that were passed from MongoT, and then it's going to return those documents back to the application. So if you look just at the left side, the application and MongoD, it looks like any other aggregation pipeline stage. Run query, get results. But underneath the hood, this is two purpose-built systems coordinating with each other to provide that capability while kind of hiding it from the user. So a really simple but powerful architecture. Let's look a little bit about how this gets deployed in practice. So replica sets are a kind of foundational building block of MongoDB. Generally speaking, you're going to start with 3 MongoDs. They're going to coordinate with each other to provide durability for your writes and high availability for your reads and writes. There's 2 ways to configure MongoT to run with a replica set. The first kind of simplest way is to run it as kind of a sidecar process to MongoD. This is great to get started, kick the tires. It's really simple to configure. You probably have some leftover resources running on that VM that MongoT can use. MongoT is going to replicate just directly from the local MongoD. MongoD is just going to proxy those requests to the local MongoT. So easy to use, simple to configure. You are risking resource contention between the 2 processes there. So both, can want to use a lot of CPU, memory, and so there is that risk of resource contention. And then also, there's some coupled scaling characteristics there, right? If you want to scale out search QPS, you want to add more MongoT replicas that can serve queries. If you want to do that in this architecture, you're going to be adding more database replicas too, which can just be expensive. So our recommended way to run search is instead to configure MongoTs to run separately, still associated with the replica set. So these MongoTs will replicate from the replica set as a whole, and that's really nice because now they're going to get high availability on those replication queries they're running against the database. And then each MongoT is going to be independent of each other. They're not going to coordinate with each other. They're going to maintain their own view of the index catalog, their own copy of the indexes, and this is good to just have a simple, reliable distributed system. Any of these MongoTs can serve a query from a MongoD. So MongoD is going to make its request over gRPC, and that can actually be load balanced using an off-the-shelf load balancer at L7 like Envoy. So the replication and query execution flows in both kind of the coupled architecture and this kind of separate search nodes is exactly the same. Same protocols, same algorithms. The only thing that's different is how MongoT and MongoD are configured to talk to each other. So saying a full connection string for the replica set here for replication and going through the load balancer. Let's talk about some bigger scale. So sharding, we wanted to make sure that both we support large search use cases and also wanted to make sure that we support search on clusters that are already sharded for their transactional workload. So quick reminder about how sharding works. We have a router up above. This is called MongoS. It's going to be responsible for routing reads and writes to the proper shard based off the request that it receives and aggregating the results. And then we have two shards here in this example. Shards themselves are replica sets, but you can also kind of think of them as a logical entity that owns a subset of the data for your overall deployment. So how are we going to support search in this case? Well, we're going to apply the same tried and true pattern we have in a few other places in the architecture, which is let MongoDB shine in something that it's already really great at. So search is going to run exactly the same way against those replica sets. You configure MongoT against the replica sets. From MongoT's perspective, it's replicating from that shard. It's serving queries from that shard in exactly the same way. There's no different configuration for MongoT if you're running in a replica set or a sharded cluster. So how's that going to work? That sounds really nice, but it can't be that easy. MongoS is going to have the magic that's going to put this all together. So let's take a look at that. Unfortunately, this is our last sequence diagram of the day. We have a few new players here. We've got the application. Now we have MongoS, and we have the two shards involved. So you've seen this part before. Run in the query just like any other query would be run. MongoS is going to receive that query and is going to issue what we call a scatter gather. So MongoS is going to know the collection that the query is being run on, and it's going to know which shards have the data responsible for that collection. In this case, it's going to be shards 1 and 2, and it's going to, in parallel, distribute those queries to both shards 1 and shard 2. Query execution on the shards is going to look very similar to it does in the replica set. So both shards are going to execute those queries in parallel. Same thing's going to be happening. MongoD is going to accept that request. It's going to proxy it off to MongoT. MongoT is going to execute that query against its index. It's going to return the results to MongoD of the IDs and the scores. MongoD is going to look up those results. And in this case, it's going to return those results back to MongoS. So if you recall, search and vector search queries are implicitly sorted by relevance score. And we want to maintain that interface here. So what MongoS is going to do when it's doing the gather of the scatter-gather query execution is it's going to do a streaming merge sort on the results based off that search score. So it can take the results, they might be interleaved, or they might be, shard 1 might have all the most relevant results, shard 2 might have the least, they might be interleaved. The streaming merge sort is going to handle that for you. Once MongoS has collected all of the results, it's going to send that back to the user. So again, left side looks like any other query, but once again, we have this kind of simple, powerful primitive in MongoT that's very flexible. It can run against replica sets in many ways. It can run in sharded clusters, flexible, scalable, simple primitive. So that's going to wrap up our whirlwind tour of the architecture. What I hope you were able to get out of that, there's obviously a lot more nuance in it, but from that I hope you were able to get a sense of how we leverage MongoDB and Apache Lucene strengths to build a great developer experience that does not disrupt your transactional workloads. There's always a bunch of exciting stuff going on in search and vector search, as you're probably not surprised to hear. From kind of the systems and architecture perspective, a few things I want to call out. Performance is always something we're really hammering on. It's the never-ending pursuit. We recently launched some exciting improvements in binary quantization for vector search indexes, the speed that that runs at. So if you're using binary quantized indexes, you should have just, on Atlas, gotten those improvements naturally. Filtered vector search queries, some query execution improvements are coming in the next few months that we're really excited about. And then the performance of the initial sync scan, we're doing some great work there. So hopefully that'll speed up how quickly you can build indexes as well. Always looking at how we can scale in new dimensions and make that more seamlessly. On Atlas, we're going to bring auto-scaling to dedicated search nodes, the tier, scaling out replicas, and we're also looking at good ways to isolate the resource consumption of index builds from the query serving workload. And then one thing I'm really, really excited about is auto-embeddings. My colleagues, Prakul and James, are going to be giving a talk later today Auto embeddings is going to take away the pain of managing embeddings for your vector search indexes in the same way that search and vector search take away the pain of managing dedicated search infrastructure. So really exciting. Go take a look at this. And also just want to call out again that MongoT that we just covered, source available on GitHub. Go check it out, and hopefully you can see a bit about what I was talking about today. I think we have a little bit of time for questions, if anyone has any. Yeah? Sorry, I think there's a microphone you could speak into.
Hi. So the result were streamed back to MongoOS, or they were bashed and it waited for both the result to merge the results?
A little bit of both. They are returned in batches, so it's kind of an RPC of returning a batch of results, but that's happening in a streaming manner. So it's continuously sending results back, but if you look at kind of the frames over the network, it's going to be a batch of results up to 16 megabytes, and then it's going to continuously send that if it needs more results.
Sorry for this naive question. I've used Elasticsearch vector search before, but how is it going to, in the performance-wise, why should I choose MongoDB?
I mean, we're competitive on performance. It's a purpose-built system. Apache Lucene has really great performance for vector search, and we've been pretty active in improving that performance. Really, what's going to be great about MongoDB vector search is that you can store your data that the vectors are based off of in the same system that's running your vector search without sacrificing anything on either side, right? We have a best-of-class transactional database and a best-of-class vector index. We're not sacrificing kind of performance or availability on either side of that.
And the search score that you mentioned, are these like prudent system that you calculate the search score?
Yeah, the question was, how does the search score work? For kind of search, it's based off BM25, which is kind of an industry standard relevance that's using, it's basically based off term frequency, inverse document frequency. For vector search, it's going to be based off vector similarity. Vector similarity, you want to minimize it, so you want a small distance between the two vectors. But you saw the scores were kind of like 0.9. We want the score to represent higher is better, so you're actually kind of inverting it in a way for vector search that kind of takes that distance calculation where you want it to be smaller and makes it higher. Yeah. Any other questions? All right, thank you very much.